Morning, and for some of you, most of from China, and good evening if you're from North America, maybe somewhere else. Welcome to the lecture 5 of the 2023 annual lecture series of Global Lecture Series on Chinese economy. And today we have a great pleasure to have Professor Kling from the Cornell University to present us something on the social costs of nutrient pollution. Let me give a very brief introduction of Professor Catherine Kling, and a very impressive CV and credential. And Catherine Kling is the Tisch University Professor in the Dyson School of Applied Economics and Management, and the faculty director at the Atkinson Center for a Sustainable Future. And she is the she was elected to the National Academy of Science. In Chinese, it's called academician, which we normally know, this type of title. She is also an elected fellow of the Association of Environmental and Resource Economists, and also the re-elected fellow at the Agriculture and Applied Economics Association. And her specialty is largely on the economic valuation of ecosystem surveys, and also on the integrated assessment modeling for the water quality. And her research program has been funded by National Science Foundation, the U.S. Department of Agriculture, the Iowa Department of Natural Resources, and the U.S. Environmental Protection Agency, among many others. And I know Catherine actually a long time ago. Catherine may not necessarily remember. We actually were, at one time in 1986, I studied in a master's degree at the University of Maryland. And I'm also, well, with the IFPRI when you served as a board member for the IFPRI. So without any further ado, Catherine, I will give the floor to you. You have 1 hour to give the lecture, then we'll follow roughly 15 minutes question and answers. The floor is yours, Catherine.
Thank you, Kevin. That's great. I admit that I did not remember you from 1986. I did remember you from IFPRI, but that was a long time ago. Anyway, yes, thank you for that very nice introduction. It's really fun to be here, not here, but to be presenting a talk like this to everyone. I'm going to go ahead and share my screen, and then I'll. But to be very clear, this is very much work in progress. I'll be talking about the various things we haven't done, as well as the things that we have done. So I very much welcome suggestions of all sorts, whether it's in chat, the questions afterwards. If you want to follow up with email, anything like that would be very, very welcome and appreciated. Title of the talk is The Social Costs of Nutrient Water Pollution. There are a great many people that are working on this project as a team. I've got a list of the primary people here: Tina Andarge, Manuel Hoke, Youngji Ji, Dave Kaiser, myself, Dan Fineff, Jimmy Schur, and Nilesh Shinde are all either economists or water quality modelers, hydrologists, that have been working on and off on this particular topic, and now on this particular large project for several years now. And we're pretty excited. We're finally getting to the point where we feel like the shape of the entire work is coming together. So thanks again for listening, and really looking forward to getting comments. So I've got some pictures there to give you some idea of what some of this is going to be all about, and it's about water. You can see a picture of a little girl swimming. That's actually my daughter from about 20 years ago. And that's going to represent the idea of water as a recreational resource. Right next to that, you see a fisherman that's got big mats of algae growth that's associated due to poor pollution, poor water quality pollution. Below, you see the impacts on animals from bad water quality. And then you see this big, large drinking water treatment facility. And that's another component of this work, is thinking about the costs associated with having to clean our drinking water because of water pollution. Okay, here's what I'm going to talk about today. Kind of give you a head what's coming, an outline. So first, I'm guessing that there's a number of people here that don't know very much about water pollution, and particularly the type of water pollution, nitrates, nitrogen, and phosphorus that I'll be talking about. So I'm going to start with an overview and introduction. Then I'm going to talk about integrated assessment modeling, what that is. I think probably more people in this audience are familiar with that, but I'm just going to kind of do a quick overview to remind you and try to place our work in the literature. And then I'm going to drill down into some of the pieces of our integrated assessment modeling. And as I said, those pieces are going to relate to recreational use of water, aesthetic value of water, that is the enjoyment we get from looking, living close to clean water. I'll be talking some, if I have time, about greenhouse gas emissions that come from polluted water and damages to drinking water sources. Okay, topic number one here, nutrient pollution, some basics. I'm going to be using the term nutrients and nutrient pollution to mean two types of pollution, nitrogen and phosphorus. These are natural. Nitrogen and phosphorus are important components of the natural system. They're part of the food web. Algae depend upon them, various aquatic plants, and that base of the food web then is critical for all other species that live in and near the water. That's animals, birds, insects, and so on. So, well, we need some of it. The problem is when we have too much. In that case, it can really affect negatively ecosystem function. If there's too much nitrogen and phosphorus, then those cause too much algae and plant growth in the water. That then algae and various plants take over an ecosystem. They choke out other types of living organisms there. They decrease the oxygen available for other aquatic life. And in really dire cases, they can cause illness or potentially even death, although that's basically not heard of much in the way for humans. And that's from things like harmful algal blooms, which can contain poisonous toxins. So basic notion is nitrogen and phosphorus are natural. They are key fertilizers and they do lots of good things, but when there's too much of them, they act very much as pollutants and externalities. My talk today is entirely US focused. So I'm going to be talking about clean water and these issues in the context of US regulations and US approaches to controlling and addressing water pollution. Many of these issues, as I understand it, are also relevant in many other parts of the world, including China, many Asian countries, definitely European countries. So while the topics and issues I'll be talking about are quite relevant, the specific context, of course, of the legal regulatory environment will be focused on the US. So just to give you a little bit of background there, the main regulations in the United States that address water come from the Clean Water Act. The Clean Water Act was passed in 1972, so that was 51 years ago now. That was passed with a goal of eliminating all pollution into water. A pretty large goal, but that was the stated goal of the law. So what has happened and what does that mean? Well, all the sources, industrial sources, so factories, drinking, wastewater treatment plants, all of those kinds of sources of water pollution were regulated with direct permits. They were given limits, they were told, and it was enforced that they not pollute beyond a certain level of what was regulated. However, a very large source of nutrients is from agriculture. It comes from animal agriculture through manure, and it comes from row crop agriculture, corn, soybeans, all different types of plant growth is not regulated. And so the situation as we have in the United States right now is that all forms of water pollution coming from factories and coming from wastewater plants are regulated, and the level of pollution coming from them has declined a lot. But that is not the case with all agricultural sources. So I want to give you a quick overview of what this all means in terms of the amount of pollution we're seeing in the United States and what we think the sources are. So this is I've got a couple of slides here that I took from a real nice paper by Dave Kaiser and his co-author. And in that work, they collected data from across the United States for the last 50, well, you can see the year period on the graph, from about 1962 to 2001. It was a huge data collection effort because this data was not in a given location. They had to collect it from a variety of different sources, and then they had to clean and make the data comparable. In any event, after a huge amount of work, what this shows is a very simple trend line. There's no model here, there's no nothing, except to show averages by year over the roughly 50 million data points that they put together for a very important endpoint that indicates water quality. And that is the share of waters that are not fishable. So what that means is a downward sloping line, as this one is, means that we are seeing fewer and fewer not fishable. The water quality is too poor to fish in. That means that water quality has improved. Downward sloping means water quality using this measure have gotten much better. It's clearly good news in the United States. If you look at the amount of pollution that is causing problems for lakes and streams to not be fishable, it has declined significantly over that 50-year period. Good news. Here's another bit of good news using a different measure of water quality. Likewise, downward sloping is good. Saturation deficit, this has to do with how much oxygen remains in the water, and how much too much a deficit. So a saturation deficit means there isn't enough oxygen. So a declining trend again is good because it means that there are much fewer water bodies that suffer from inadequate oxygen levels. So good news, all good news. What they report is that this sort of trend information for a whole host of water quality endpoints. What I've done here is taken their data on nutrients, nitrates and nitrite are two forms of nitrogen, a pollutant. What I'm showing here is nitrates, a 50-year trend over many data sources. The slope is 0.002, not significantly significant, which is to say that over that 50-year period, there's no change, statistically speaking, in nitrate levels in our water bodies. That's not good, because there's always been too many of them. Likewise, nitrite, another form of nitrogen, actually has an increasing coefficient, but in fact, it's significant. So not only is it not declining, it's actually significantly increasing. So despite the enormous gains we've seen in some of those other important endpoints, nitrates and nitrate are not going in the right direction. If you look just below the blue circle, you will see that overall nitrogen has declined, and that's a good thing. Likewise, overall types of phosphorus have declined, but by very small amounts. This is another slide that talks about the situation with respect to nutrient pollution in the US. This is summary data from the US Environmental Protection Agency that shows nutrient pollution affecting 46 and 45% of the lakes in the United States. So almost half are in poor condition and only about 40% are in good. Bottom line is we've made huge improvements in water pollution of many types in the United States. The one type of pollution we have failed to make progress in and has appeared to even worsen is nitrogen and phosphorus. All right. So today, what I'm going to do is now, with that overview, and I hope you get the take home that we're still struggling from too much of this type of water pollution. I'm going to now start to talk about the modeling that we're doing. And in the hopes that it'll help provide context for people that know some of this literature, and if you don't, that's okay too. But I'm going to talk initially about integrated assessment models. IAMs is the short term that gets used. People that work in environmental economics would be very familiar with this terminology. Others might not be so familiar. The basic idea of an integrated assessment model is to bring economics, and in this case, damage estimates, marginal damages, marginal costs of a pollutant and externality, to bring that economic information and connect it with geographic and the physical science associated with the issue. In this case, the physical science we need to work with and the scientists that we've worked with are hydrologists and water quality modelers. Ultimate goal of one of the simple ultimate goals of an integrated assessment model is to construct gross external damages. The idea being, if we know how much pollution, emissions of nutrients are coming in different points across the landscape, and we know what the marginal damage of those are, here I'm abbreviating that marginal external cost. If we multiply those together and add them up across all sources in all locations, we can get an estimate of the externality damages, the gross external damages. So that's that's the simple idea of what these models are about, what we're looking for. The literature has a bunch of them. A very great, a really nice example is Nick Muller and co-authors wrote several really nice papers on conventional air pollution. So this is pollution of particulate matter and emissions from power plants and elsewhere into the atmosphere that then moves from its location to where people are. When it drops on people, it imposes health damages, visibility damages, and so on. And Muller et al. Monetized. They estimated the marginal damages, the marginal cost of those damages, and then were able to take account of the science concerning where pollution is located, how it moves through the atmosphere, and what the impacts are ultimately. There's a number of integrated assessment models in climate. That's probably the most important or the most well-known area. So things like the Dyson model are of this very ilk. The social cost of greenhouse gases, the social cost of carbon comes directly from those kinds of models. There's some work in water, but the bottom line is we don't have national scale integrated assessment models for water. And the goal of our work is to fill that gap. Here's a slide that gives you more detail on what it is as we build our model that we're doing. So if you start, I'm going to go back and forth between the numbers in the steps and the little picture on the right. We're going to start with emissions. These are the externality, nutrients. They come from agricultural uses or uses in cities, so to fertilize, for example, golf courses, and some of them still come from industrial sources. So we're going to figure out where all those emissions are, and that gives us land use and emissions. We then have to link that basic core data layer to the hydrologic system, the movement, the way water moves from where it starts, where the pollution enters water on the landscape, and then moves down rivers, around lakes, where it ends up going. Sometimes that's referred to as fate and transport. But we are working with hydrologists to model that, because we have to know, in order to do this work well, we have to know where the emissions come from. Then we have to know how they move through the landscape. Then we have to know where they end. And when they end somewhere, we need to understand what the impact is. That goes under the terminology of looking at the effect of ecosystem services. What do people care about that this pollution affects? Recreation, the visibility, how nice it is to look out your house at a lake or a river. It can have health effects. It can have effects on the cost of drinking water and more. Those are the ecosystem services. Those are, you can think of as the goods that we're thinking about from an economics perspective. And then the final piece is to monetize. What is the value, the economic value of those components? We are doing an integrated assessment model in a bottom-up approach. What I mean by that is we're thinking about each of those individual ecosystems, services. Water, clean water we use for drinking. Clean water we use to enjoy. We fish, we boat, we hike along it, we swim in it. We use these for what I'm just going to refer to as amenity aesthetics. So lots of people like to live near nice, clean lakes. They like to see wildlife. They like to see a lot of enjoyable things along those lakes and rivers. And there's also other services relating to the generation of greenhouse gases. Okay, let's get to some simple economics then. I hope that gives you the concept, the big picture concept of what we're after. I'm going to start to lay out our modeling structure, the way we're thinking about integrating these different components. And in particular, I'm going to try to focus on being careful that we don't double count values associated with different ways in which we're estimating our marginal damages. So first, high level, think about a landscape. I'm going to show you a map of the entire United States next. That is going to be the landscape that this model covers. It doesn't have to be the whole of the US. It could be the whole of China, or it could be a small area. But just think about a landscape, a place. And think about that place having bunches of areas where people live, residential locations. We could also just call those neighborhoods, places where there are houses. In addition, think about that landscape having water bodies. You can think about it as lakes. That's mostly what I'm going to be talking about, but water bodies in general. So there's a landscape. It's got places where people live on it. It also has places where there are lakes. In addition, we want to think about, we want to think about the quality of the water in those lakes. So we're going to use QJ to indicate ambient water quality. And ambient just means the water quality in the lake, what it is there. We measure ambient water quality a number of different ways: how clear the water is it risky to swim there, and so on. But the ambient water quality relates directly to the amount of pollution, the amount of nutrient pollution. So here I'm using E as nutrient emissions. I will be calling them nutrients. What I mean is total nitrogen or total phosphorus. Those are just the abbreviations. For purposes of thinking about what we're doing, you don't need to know or understand that. When I say nutrients, I'm thinking both nitrogen and phosphorus. Now, this is where the science part links. We need to be able to relate the quality of water in a given lake to the emissions of nutrients in different places on the landscape. You can think of this as a production function, a water quality production function. The water quality in a given location, J, on the landscape depends on the emissions of nutrients at that same location. So one of the J's will be EJ, as well as emissions everywhere else on the landscape, because it moves. Right? Water moves, and so you can have pollution far upstream, and that can impact the water quality in a local lake. Very naturally, we can think of the marginal product, which in this case is a negative thing, but the derivative of the quality with respect to emissions, you can think of as the marginal change in water quality from a change in emissions loading in another location. As I said, we're doing the entire United States. So this is the landscape we're thinking of. What you're seeing here is a map, obviously, with water bodies, the particular water bodies being lakes. So these are all the lakes. Every little one of these dots represents a lake. There's about 30,000 of these lakes. And we're looking at lakes greater than 25 acres, about a kilometer square or larger. Another piece that we need is the initial concentrations, those Qs. Remember, I talked about we have a production function. The quality depends upon the emissions. So we need that emissions. We need to know what our starting baseline of nitrogen and phosphorus is across this entire landscape. In 2020, a really nice paper was published. The citation is down here, Shen et al. And what they did is bring together an enormous amount of data, just like the Kaiser et al. Work, where they identified the locations of nitrogen and phosphorus. They used machine learning techniques to help make this data match and talk to each other. And in short, here's 4 maps taken directly from that paper that show where nitrogen and phosphorus concentrations are high and low. This is the pretty little chloropath, key. Bottom line, for our purposes, this gives us great coverage of a baseline water quality that we can then use to build our model. We also need people in our model. So for the people, we use census tracts. There's about 73,000 census tracts from the 2010 census. That's where our people are in all of this. We also need and do have a relationship between the water quality and movement of water across the landscape. So what you're seeing now is the United States divided up into watersheds. So each one of these little circly things in here is a watershed. Watersheds are connected. This gives you an example, and 18 examples, in fact, of the relationship between a watershed and its downstream cousins. So, for example, I've got my little clicker over a red watershed, a watershed that's covered in red in Texas. What this map is showing you is that if nitrogen and phosphorus are emitted, if there's pollution, nitrogen and phosphorus pollution that starts in that red area, it will move from that area down to the next watershed, these lower levels of blue watersheds, ultimately until it drains into the Gulf of Mexico. As it moves, it degrades. So if you have a ton, say, of pollution, nutrient pollution here, a full ton will not end up all the way downstream. Something less will. There's a process, a physical process of degrading that we need and will have as part of our modeling. Okay, so that's kind of the big level structure, the core data layers that are going to build our whole model. Let's talk some more about the economics. We need to think about damages. We have an externality. We want to think about the welfare effects, the welfare consequences. And we want to do it in a way that imposes as few assumptions as we can, and then gives us the insight from theory about how to build this nationwide model. So I told you to think about those large N places where people live. So we're going to think about residents, households, picking one of those locations, one of those N's to live in. They're going to pick a housing location. When they pick that location, they're effectively, by doing so, choosing the neighborhood amenities and public goods. Those of you who are familiar with hedonic models will be very familiar with this story, or some of the urban land use models. It's the idea that people choose from a variety of options in order to maximize their utility, of course. And when they choose a location, they're effectively also choosing public goods. One of those goods is that they are choosing, by locating in a certain neighborhood and a certain location in their neighborhood, how far away they are to the closest water body. And we're going to think about that closest water body as being the one if there is even one close to them, that provides these amenity services I talked about. If you're right next to the lake, you look out on the lake, you get to see pretty water, you might get to see wildlife, you might get to see boats sailing by, and so on. So when you pick your location, you have chosen how far you are from the local lake. This creates a hedonic price function. And what you see, the notation here is P. That's the price that a house transacts for. And we're going to assume that there is a well-functioning housing market so that the price of a house reflects the distance to the local lake N, just the one lake that's nearby, the so-called amenity lake, the current quality of that lake, and everything else. Okay, so that's just the notation. So they select a location in the landscape, and now they have a house somewhere. Okay, so they've chosen a location for a house. Let's think a bit more detail what that gives them. It gives them these amenity services. So I'm now going to make a new variable that we think of as the bundle of amenity services that they get from distance to the lake and the quality of the lake. By choosing this location, they have also effectively chosen their location to all the other places they might go if they want to get in their car and drive somewhere to spend a day at the lake. Recreation trips. Oop, gosh, I'm sorry. I moved my my clicker and it all moves. Of course, they have income. We have some numerous spending, and we also have costs. Normally, I like to use P for the price of something, but we have P for the hedonic price function. So now we're going to use C for cost to visit the recreation sites. Okay, now we've just written down a slightly more formal utility model. It's very simple, even though it's got a lot of subscripts and jazz. Household utility depends on the amenity value it gets from the house it chooses. That depends on its location. It gets utility from the vector of X's, the goods, recreation, how many visits, if any, the household takes to recreation site 1, how many all the way up to recreation site J. But we're specifically noting that visits to those locations is dependent upon the water quality at that location. Public goods and everything else they buy, the Z. They, of course, face a budget constraint. Income depends, must balance the hedonic price for their house plus the costs of driving and participating in lake recreation. I've made this slightly uglier than it needs to be by separating out the component of costs associated with visits to the recreation site that is also its amenity lake. That's the lake right next to his house versus all of the other. And the reason I'm going to do that is, I'll show you on the next slide, because the first thing I want to think about is how to measure the marginal damages associated with the amenity. Remember, we've got a utility that depends on amenity. That's the good. That's just a good in the utility function, and recreation. So this whole thing here is just a simple repeat of what I had up before, just so it would be on this slide. But now what I want to do is think about what's some basic first order conditions with respect to the components of the amenity good. The amenity good depends on the distance to the local lake and the quality of the local lake. So all you see here is some first order conditions. The first one here is the first order condition with respect to the quality at that local lake. The second one is the marginal utility first order condition associated with the distance to that local lake. If you stared at this for a minute, you would see that by substituting in the marginal utility of trips equal to this cost times dn, that this term simplifies to the one you see at the bottom. And what it says is that the price gradient, that is the change in the hedonic price function as water quality changes, the household will set that just equal to the marginal utility it gets through the amenity pathway from that cost. Nothing surprising here for those, or really anybody. What all this really means is that they'll set the price, the marginal price, equal to the marginal benefit. It then allows us to directly think about what we need to do in order to monetize the marginal damages. Well, what we're going to need are the components of the pieces that will allow us to take the change in the house price, that marginal cost, and grade it over all the prices, all the houses. Summary of that is what we want is we need to have the how do the home prices change with the change in water quality. That gets at that first that slope. How do when we have a change in water quality, how does that change the price of a house? Then we know what we need to know. What's the starting price of those houses? Okay, market value. And finally, then we got to add it up over all the people in the market. Okay, so we're going to change the water quality at all the lakes a little bit, see how that would change prices, and then add it up over all of the prices, all the houses. There's a lot of detail on this slide. I'm just trying to give you the flavor of what we're doing. This gives you the details, some of the details about how we have actually done this. Again, for those of you who are environmental economists maybe and know the sort of lingo, essentially what we're doing here is a large benefits transfer. We've taken estimates from a very recent and really nice paper. I can say that because I'm a co-author, just published in the Proceedings of the National Academy of Sciences, that looks at and estimates the relationship between water quality and house prices across the entire United States. That's the key economic piece we need. We need that elasticity. When water quality changes, how much do house prices go up? They fit models using about 675,000 transactions across a large number of lakes. And from those models, they generate the elasticities, as I said, that we need. For properties that are close to water bodies, they estimate that there is an elasticity of 0.16. So for homes that are close to lakes, a 1% change in improvement in water quality leads to a 0.16% increase in house price. When you look at house prices that are a little bit further distant from lakes, not surprisingly, you get a smaller response. It's very intuitive and something we've seen a lot elsewhere. With that, we then take the data that is available to anybody to figure out how many homes in the United States there are in those bins, turns out that there's 3.36 million homes within that band of 300 meter. And we know what their current value is, their assessed value. Now all we got to do is construct the predicted changes in prices times the number of homes and their location within 300 meters of lakes. And here's a map of where those homes are. And then we can monetize them. So here is my first result for you. This is an example and a finding, I guess, an example of following this procedure for a hypothetical 10%, so counterfactual 10% improvement in water pollution. That is a 10% reduction in nutrients in lakes across the United States. So this is just a counterfactual. Let's just imagine that overnight, there was a 10% improvement in nutrient water pollution. What this method and model finds is that that translates into about $230 million annually in benefits. So $230 million annualized benefits. It comes from this counterfactual. That roughly is $68 per house per lake, or per house per household of people within that 300 meter bin. Okay, that's a piece of information that we then want to use to aggregate up in our integrated assessment model. But that's not all, because that amenity value is only one of the values that we know come from water quality. There are others. And a second one that we know is very large is recreation. Now, I am not going to talk you through all the pieces like I did of the model for stored conditions and so on. There isn't enough time and it gets kind of boring to see that anyway. But I wanted to do that on the first one to give you the sense about how we're doing this based in theory and then adding back up. And I am going to highlight the one result that is important for recreation. I'm going to skip this. And yeah, I guess I'll, yeah, okay, I'm going to make you look at this one more time really quickly. Then I promise I'm done. The key reason I wanted to show you this, as I said, is we need to be careful that we're not double counting. And we want to be very careful that we're not double counting benefits from water quality improvement, both as they capitalize into a hedonic model and as they would show up in a recreation demand model, which is the next source of modeling I'm going to show you. And so the purpose of this set of first order conditions is to show that, in fact, the hedonic price function will, in fact, capitalize and capture the distance component associated with living near or far a lake, but it will not capture a change in the water quality. Because neighborhoods, just intuitively, people purchase a house when at a given water quality level. So that's the water quality level that capitalizes. If there is some change, then that will not be capitalized in the house price, but the residents may visit that more often to recreate. Okay, I'm going to now just jump right into giving you how we actually go about the recreation. I'll give you results, and then we'll have some time for discussion. Okay. We again, this is a slide that talks through each of the pieces that we need in order to create a national scale estimate of water quality damages. One thing we need is a relationship on recreation. We need to know if we change the water quality. So I'm using new water quality here now. This is nitrogen and phosphorus. If we change that, how much change does that make in recreation trips? You can think of this as a dose response function, actually. Dave Kaiser, one of my co-authors here, wrote a really nice paper using the National Survey on Recreation and the Environment for a 20-year period to fit that exact relationship. It's a national scale model. Using that model, he was able to estimate that with an increase in water quality, you get an increase in visits. If you make water quality worse, a 10% increase in pollution, then trips decline. That effectively gives us the elasticity we need in order to construct nationwide estimates. What I'm going to do now is simply jump to the answer for recreation. We find that annually, for a 10% improvement in water quality, remember this is the same improvement as I showed you for the amenity values capitalized into hedonics, we get $5.6 billion a year. That's an order of magnitude higher than what we had for the amenity value. Now, excuse me, what I'm going to do now, so we've got two numbers. One thing we can do is just add them together. And we've been really careful so that we aren't double counting. But I've missed telling you an important part of the story. I'm going to tell you the important part and then give you the final slide with results. The important part of the story I did not tell you is about the movement of pollution. I told you I was going to at the beginning, but what I've showed you so far is only estimates of the damages, the pollution damages that come from the local 10% increase in nitrogen and phosphorus. In other words, it doesn't take into account the science that if you increase 10% in a given location, here I've got a little one of these many watersheds that we've got a blow up of. If I increase water pollution 10% there, it will damage recreation use in this sub-watershed, and it will affect the amenity value. But it will also cause damages downstream. And the numbers I just showed you only showed the damages to each watershed. It did not show you the downstream effects. So what I'm going to show you now as the last set of estimates is estimates that include only those local damages for 18 of these sub-watersheds. Remember, this is the exact same map I had up here before. There's 18 red sub-watersheds. And then I'm going to show you how those damages increase when you recognize that there isn't just damage where the pollution occurs, it affects all of these downstream. Now, I wish I was able to show you this for more than these 18 watersheds. And not only am I showing you the 18 watersheds, because we still don't yet have the full model working to connect every watershed to its full downstream. So what you're getting now is just an indication of an example of what we are finding, and we hope to have a full set of numbers by this summer or fall. So I gave you estimates to start with in the last for recreation and hedonics for the entire US. If you reduced nutrients, that is, you improved water quality everywhere by 10%. Now I'm showing you those, first take a look at this first row. I'm showing you those same results, but this time only for 18 sub-watersheds. This is not for the whole US. This is just 18 small ones. And I'm calling those the local estimates. One thing we can do is add them up. The other thing is we can take our local and downstream, where we now include not just the damage that occurs in those 18 watersheds, but also the damage from following through as that pollution moves downstream. In these 18 example watersheds, we see that they're, for recreation, we go from about 148 million in damages to 218. Okay, so about a 30% increase. For amenity values, we go from 6.4 to 9.4. Again, well, that's more like a 50% increase. Again, these are just those sub-watersheds. Yep.
Just want to give you a quick alert. You probably have 5 minutes, or
Perfect.
you can have a bit more time, 10 minutes maximum. Just to give you an alert on that. Yeah.
Thank you. 5 minutes is perfect.
Great.
In fact, three will do it. So those are the main results I wanted to share, and I've gotten through them. The one, we are working on additional components. As I mentioned, I'm not going to show you any of those results. It would take too much time, and I'm hoping I even got the main idea of what we're trying to get across here. What we are trying, we are also going to be looking at is greenhouse gas emissions. I'm showing you that just to see the title. And we're going to be also looking at drinking water. Okay, so these abatement costs to drinking water systems. So I talked through 2 of the damage components. There's 2 others that we have pretty much, well, we have ready, but there's no need to go through them all. And then that's just going to take me to my last slide, which is to thank you and to just say that what we're after here is to construct a integrated assessment model for water quality, analogous to the social cost of carbon model that we have for greenhouse gases and the air pollution models. We need it to incorporate the key services, the key goods. We want it to be very based in theory, so that when we aggregate, we think carefully about the economics and double counting. And I thought I would just end with this quote from EPA. It's on their one of their main websites. I got the link to it here, that nutrient pollution is one of America's most widespread, costly, and challenging environmental problems. We're hoping with this work that we are going to really be able to help talk more specifically about just what those costs are. With that, thanks, and I'm happy to have comments, questions, however you all like to do this. Should I stop screen share?
Since we're going to have some questions, they may point to your PPT. You may want to leave that on, if that's okay with you. Well, Catherine, thank you so much for this incredible presentation, and it's extremely valuable. And even though your work is based on US data and so on, and China certainly is faced a very similar challenge. I remember when I was in Maryland in 1985, and the people there talk most on non-source point pollution from agriculture and so on. China certainly started to talk about the non-source pollution about 5 or 10 years ago. And now they are very much in a big way trying to reduce the nutrients pollution in the different water, rivers and the lakes and so on. So one of the challenges is really how we assess those impact, particularly from the social side. That's what is very much lacking in terms of come up with the value and to guide the policy making, and also the data issue. What you presented here certainly give us almost like a very nice blueprint. What China could do actually. I'm not so sure whether we have all those data, but certainly maybe we can try at some smaller scale at first. But anyway, we have a couple of questions already in the chat box. I'm not so sure you can read the chat box or not. If not, I'm going to read those two questions to you. You can respond. And for the audience, if they have a question, they can raise their hand. They can also ask the question directly. But let me get those two questions which are posted on the chat box first. One question, Catherine, is asked as follows. A large part of nutrient pollution comes from agriculture. Is the coincidence degree between the water pollution map and the current agricultural planting map relatively high?
Yeah, a great comment, good visualization, and it is certainly, it's very causal, yes. Agriculture pollution is the single largest source of nutrients, and it's somebody that clearly knows the U.S. ag system. The big places where there's lots of nitrogen and phosphorus, it is also the biggest agricultural regions. This whole central part of the U.S. is heavy maize, corn, and soybean rotations. It's a very heavy user of fertilizer, and it's unregulated. And so there's just an awful lot of fertilizer going on, and it ends up, some of it ends up not being taken up by the plant, but in the streams, rivers, and moving downstream. So exactly correct. And part of what we're kind of hoping to look at is to sort of say, well, what are the costs of this?
Thank you, Catherine. Well, you mentioned those agricultural pollution and is unregulated. Is it still unregulated those days in the United States?
Yes. Let me be a little clearer. So the only agricultural type of regulation are what are called, they're large animal operations. In the US, they're called CAFOs, combined animal feeding operations. So if you have a large hog factory or a large chicken factory, poultry, that has over, like, I think 100,000 head of animals. So these are really big ones. They produce a lot of manure, and manure is a huge source. That agricultural source is regulated. They have to have permits, and they get inspected. But that's the only type of agriculture that's regulated. So in the United States, and the person who asked the previous question, I'm sure would know that about 40% of the entire land area in the United States is agriculture. I actually, it's probably really big in China too. I don't know. I should look it up. And that's for growing. If you're growing plants, if you're growing wheat or maize or soybeans, there are no regulations, none, completely unregulated. And that has to do with the way that the federal law was created. They said 50 years ago, states should be the ones that regulate, but states, almost no states actually do any regulation. And if they do, it's very small.
I see. Well, thank you so much for clarifying this. Let me move to the second question raised in the chat box. The question read as follows. The relative pollution levels of nutrients in different watersheds vary. So are the treatment methods different in each region?
Yes, but not. So yeah. So first answer is yes. They are different. They're and what's different is not only the. Let's stick with agriculture. Okay, it's not only what's being grown. So across the whole middle of the country, it's pretty much the same thing. It's corn and soybeans. There's a lot of options that, but some of those treatment methods will be better, more cost effective in some parts of the Midwest. Specifically, when it gets a little bit to the northern part, it's a little wetter and colder. And some of the treatment options don't work as well. Cover crops is one of them. Cover crops means you plant another crop to keep the soil covered over the winter, and then you kill it off before you plant in the spring. That works in warmer environments, but it doesn't work very well when you get further north. So that's an example of, even when there's the same kinds of crops being grown, there can be really different cost-effective, the treatments can be very cost-effective. In addition to that, in some parts of the country, there's different things being grown. So Florida, if you know where Florida is, it's the southern part of the US. What they're growing is not corn and soybeans. There's some of that, but some of it is sugarcane and other things that have very different production processes and different approaches to treatment. So yes, it's a great question. There's the treatment costs differ and the effectiveness differs. So if we're designing an efficient policy, we of course want to take all of that into account. We would want to be thinking about what are the various most cost-effective approaches in different parts of the country.
Catherine, I read one of your early paper on looking at the near channel management for treat the water pollution, nutrient pollutions, where you propose that this is the most cost-effective approach. And recently, just last week, actually, I visited in China, Jiangsu, where is the rice grow regions. They certainly built a lot, first, the second, and the third small stream alongside of the rice field to plant different type of plants to clean the water, water circulated, and so on. But when I look at those, the costs seem to be enormous, right? So I'm wondering how feasible to, for example, to diffuse this kind of management infrastructures and so on. So I'd like to hear your comments on that, which is very related to the second question, which I call from Box.
Yeah, you bet. I think that's cool. Thanks for having read the paper. I think the paper you're referring to is one that relates to northern, the Minnesota region, which is actually a good example of what of this exact point. It's in the northern part of the U.S. And in that part of the U.S., that body of research suggested that in that area, that local area, the most cost-effective way was this near channel management, that particular treatment option. That would not necessarily be true in other parts of the country. So, but you then go to the next question as an economist. Okay, well, suppose you've identified what the most cost-effective, the cheapest way you can do it is. That doesn't mean you should do it, right? That can mean it's more the marginal costs exceed the marginal benefits. And that's, I think, a question that is we as economists need to do our best to help answer. there will probably be some places where it's too costly to clean it up. We don't have good technologies, and we're not willing to give up the food production and so on. Other places we will, and so that's part of the whole thinking about, being efficient. Is that kind of what you're trying to get at?
I think so.
Yeah.
Well, I'm going to take advantage of being a moderator this time. Just follow up a question on the benefit side. You're talking about benefit estimations and so on. So I guess the question which I posed is also very much related benefit you can get of improving the nutrient situations in the field, right? And if you can get a larger benefit, then problem is how you actually estimate those benefits become quite challenging. So you did mention how you measure that using the housing price and so on. But I guess it depends on how efficient or the housing market is and how regulated that is as well, right? And so in one country like US may be very relevant, and but in others like in China or maybe in other developing countries may not necessary. So in this kind of case, well, how would you come up with the estimate for the benefits, right?
Great question.
Yeah.
So there we have. So I don't know enough about the details of China, so I'm not going to even try to be specific. But you're absolutely right. You need efficient housing prices in order for them to believe that they, in order for them to get, for evidence to be that these values show up in the price of houses. If you do not have, houses that buy and sell in a pretty open market, free market, you're not going to get that. So you're exactly right. And if that's true in China or in other places in China or in other, then you're absolutely right. You couldn't use that method. That method only gets at one piece. There are the recreation part in the US is a big part. People get in their car, they drive, they spend the day at a clean lake, they drive home. Getting data for that, in fact, that's the largest part that we're finding so far. That may be, and that's a second piece that we're adding up, may be much more appropriate to be thinking about for China or other locations. And third, stated preference methods, continued valuation, if done well, are also perfectly capable of estimating defensible benefits. What is best for a particular country, a particular group of people? I wouldn't try to say in a quick webinar like this, but there are certainly other methods that potentially could work.
Well, thank you so much, Catherine. And I know that some audience may have questions, but given the time, we are very much close to the end. So I probably like to take this opportunity to thank you for very excellent presentation. I think it's give a lot of food to thoughts what we could do, and I'm sure some of the audience may follow up with you directly in the emails and so on. And well, I know you visited China last time. There was, if I remember correctly, with the board of the IFPRI, that was almost 6 or 7 years ago now. Yeah. Right. I don't know whether you had a chance to come back again, but if not, I hope we could invite you back. And there's a lot happening in control the non-source pollution in the agriculture, because as you said, just like in the United States, China now seems to control the industrial level, municipal level source of pollution quite well now. Now the attention goes to agriculture. And they now realize agriculture become the most important contributor to the pollution, to the lake and to the river. So a lot of efforts try to devote it to that. Yeah. So your research will be very relevant and will be very timely. So I'm very much looking forward. I hope we can bring you back to China. And I know you had a little vacation last time. You can have a second one this time. So let me take this opportunity to thank you again, Catherine, for wonderful presentation and the discussion. I know it's very late in your time.
Yeah, it's okay.
Let me stop right here and thank you again. Also thank to all the audience. We are also broadcasting this presentation online, so I'm not so sure how many are listening, but I'm sure quite a bit. So thank you again, Catherine. It's good to see you. Yeah.
Yes, it's great to see you, and thanks everybody. And just a final word, I'd love to learn more about the kind of work that's going on there. If other people are doing work in China related to this, I would be really excited to learn more. So please don't hesitate to reach out. Thank you, everybody. Bye-bye.
Thank you so much. Good night.